So today we have the pleasure of having Alessandra here, all the way from Verona, or Stratford. All the way from Stratford. Okay, and she'll hi. So she'll talk about topological quantum computation. Thanks.
Thank you. And thanks for inviting me, of course. Yes, okay. I want to tell you about topological quantum computation. I don't know how much you know already about this paradigm, but this talk will be quite introductory. And of course, if there is something that I say, and please ask me if I say something that you don't know, you want to know more about. Okay, so why I want to talk about topological quantum computation? Of course, I'm not a physicist, so I won't tell you about the physical aspects of this computational paradigm. I will just somehow give you an idea, tell you what I understand from the physical point of view, but what is more important for me, and also probably for you, because we are computer scientists, is to see how to use this topological feature of some particular physical particles to do computation, quantum computation. More importantly, and that's what I want to present today, is to formalize this kind of calculus, to give a kind of formal calculus, because as for classical computation, it is important to have a formalism in which one can reason about complexity, computability, and then from there move on towards the design and implementation of programming languages and all things related to computer systems. So before introducing the topological quantum computation, I want to tell you about the main objective of this work, and that I already more or less anticipated. So my aim is to define a formal calculus for this computational paradigm, and I want to use this formal calculus to address issues like quantum computability and complexity, and capture the essential mechanism for quantum programming, and therefore set the base for the specification of quantum programming languages, and the design and the implementation, and the study of quantum time systems. And there are a lot of other things that one can think of, developing this. Of course, there is the issue of quantum information, quantum communication. There is also something that is a little bit more for complexity theorists, or which is to understand the real power of quantum computation. And for this, of course, you need a formal basis, and also from a physical point of view, to understand how to use the particular features, physical properties of some systems, in order to develop new algorithmic techniques. That is now an important problem in quantum computation, because nowadays there are only essentially one technique for achieving exponential speed up with respect to classical computation. I will talk a little bit more about this, which is also the motivation of this work, but first of all, this is the plan, so three points essentially. I want to tell you about quantum computation and quantum algorithm, give a very small introduction just to get the basic idea of what we are talking about. And then I will introduce topological quantum computation, and then the calculus. The calculus is an ongoing work, so I mean we can discuss about that more later. Okay, this is a very schematic introduction to quantum computation. I think that the best way to understand quantum computation is to compare it with classical probabilistic computation and see what the difference is. Quantum computation is essentially a probabilistic computation in the sense that the results are probabilistic, so just like classical computation. The difference is essentially that in quantum computation we work with complex numbers instead of real numbers, so not probabilities but quantum amplitude that are complex numbers. So these are two computations. This one is a very simple probabilistic computation. So you start in the initial state, 0, and then you have that with the probability 1/2 you can go to state to this state, and with probability 1/2 you can go to this state, the blue state. Okay? But then again, from the red state you can go again without probability to the blue state or to red state. And the same also from the blue state, you can go without probability to the red state or a blue state. Okay? Now, we want to know what the result is of this computation. The result is essentially to say what is the probability of reaching, calculating a red state, and what is the probability of reaching a blue state. Okay? So obviously, the probability of getting a red result is 1/2 plus 1/2 from here. 1/2 times 1/2 from here. So 1/4 from this part, and 1/4 from this part. And therefore the probability is 1/2. And you can see that with the same probability, we also have the result, the blue result, because you get this result from this path, so with probability 1/4, and from this path with probability 1/4, and therefore with probability 1/2, which is 1/4 plus 1/4.
So it's a Markov chain. So
yeah, it is a
on the
Markov
previous.
chain. It is a very simple. It is a very simple Markov chain. Yes. Okay, that's probabilistic computation, very simple one. Now we can try to do the same thing in quantum computation, but this time we have to use a complex number. So, for example, these are just some examples. I'll make it a little bit more complicated, but it could be that you can have 1 over square root of 2, which is not a complex, which is a complex number, but also so you can consider this complex number, this amplitude, and then in this computation you move from the initial state to this red state with this amplitude, which is a complex number, and then again with this amplitude to this state. So I just label the branches with this.
So it's not actually the Born amplitude. The Born amplitude, would, I guess, would be the square magnitude. It'd still be 0, but
these are quantum amplitude.
But not the final probability.
No. No.
No, yeah.
In order to get the probability,
Probability,
then
you
you have to
yeah,
get
yeah.
the square root of the.
So I guess it's
sorry,
not
sorry, I
strictly
didn't
a
say that.
probability at this stage.
So,
yeah.
so they are called probability amplitude
Yeah.
because they are complex number.
Mhm.
In order to get the probability, then you have to do the square root of the
Square.
Square.
The square.
Mhm.
The square. Sorry. Yeah.
Yeah. But at the end, that's a probability, right? I mean, on the branches, it's not. Those are
Yeah.
amplitudes. But at the end, the probability of 0, she said.
At the end,
because she squared
I
them.
did
But
the
it's only
square.
squared because of the Markov chain, isn't it? It's not squared because of the Born amplitude.
So the square.
Also,
you
you're
do at
saying
the
she's
end.
multiplying.
So you should have
Sorry.
another square factor.
Ah,
in
then
there.
you
Sorry.
should have another square, maybe.
No, sorry. Let me explain. So these are amplitude. In order to calculate the final result, I first multiply these two complex number before squaring it, because the probability, I only get the probability at the end. Otherwise, I would just get classical computation, and that's the main point. So when I multiply these two complex number, I get here a complex number, which is 1 minus I. And let's do this. And then when I multiply these two, I get 1 plus I. Okay. Now I have to.
No, but the thing is, actually, you get the squared, right? When you multiply.
Where's the factor?
No,
four?
first you multiply,
It's gone, but,
and then you get a complex number. Then you do the
it's
square.
quite by
No,
zero.
no, but just if you multiply those two branches, you already get a square, right? 1 minus I squared.
Yes, yes.
Divided by 4, and then you have to square it again. Right?
Yeah,
To get
yes,
the
yes.
problem.
That's what
Yeah,
they were
I did the calculation,
And
but
the
you
four,
can do
yeah.
that by yourself. Now,
has to be
if you
four
if you do this calculation, this is 0, which means that you reach the result 0, the red state, with probability 0. Okay. So in this case, we just reproduced this computation in the quantum setting, and then one of the results disappeared completely, and that's and that is obviously because complex number can be also negative, and they can cancel them out when you sum them up. Okay, and this is not something that you can do with probability. Okay, so you never would any result here would disappear. Here we get result 0 with probability 0, which means we'll never get result 0. That's essentially what is called quantum interference, and this is the main quantum phenomenon that is used in quantum computation in order, and this is at the base of the exponential speed up, together with other features like superposition, in order to get. Okay, so this is a very simple example of quantum computation, and is actually a kind of reproduction of what is called the double slit experiment, which is one of the first experiments that where quantum interference was revealed. I don't know how many of you heard about that, but I mean, it's a well-known.
Can I just make actually something, because it's a very nice picture. The thing is that it's nice that this is basically a double slit experiment, that you have interference. But when you have it interpret this as a Markov chain, there there's one
No, you
problem.
cannot interpret this as a Markov chain.
You cannot.
No, because these are not probabilities.
Ah, okay.
These are complex number, and the problem is not the problem, but if you would measure at each step in order to get probabilities, then you wouldn't get quantum interference anymore. So you would get classical. Okay.
Yeah. So the reason, of course, is because conditional probabilities exist only between observables which commute.
Mm-hmm.
So, for example, what is the probability of 0 given that on the input was 0? That probability, if the variables, observables don't commute, this probability actually doesn't exist.
Yeah.
There's no conditional probability.
Yeah.
But of course, interference.
Yeah. So we're going to talk about commuting.
So it's important that this is not a Markov chain, whereas this is.
Exactly.
But this is
exactly.
something
Yeah.
else. Yes.
So you can always get a classical computation if you measure at each step, which means you get the probability at each step, and that would be classical. But if you just let the system work in what is called the quantum coherence, so without disturbing the system, measuring or and then just measure at the end, then at the end you get results like this that relates this phenomenon like quantum interference. Okay. So essentially, this is, if you like, quantum computation, and especially this phenomenon of quantum interference that is at the base of the only, or maybe one of the few quantum techniques used for defining algorithms that are much faster than the classical analogs. So the quantum Fourier transform is based on I will not explain in detail this, but you can see it as a discrete Fourier transform on the amplitudes of a quantum state. So this transformation allows to somehow to amplify the probability of a solution, if I can say in a very general way, so to say, and this is the basis of all the algorithm, especially one that is well known. Probably you know about that. This the algorithm for factorization that was invented by Peter Shor in 1994. This is exactly based on this idea. It is exploiting quantum interference and superposition, and it allows to get the factorization of large numbers in polynomial time. There is no classical algorithm that can do this in polynomial time. All the best algorithm for factorization are super polynomial.
If P doesn't equal NP, of course.
Well, there's no known algorithm. I'm sure there is an algorithm for factoring numbers in polynomials.
You're sure?
Sure.
So you think
but there is a chance, of course.
Yeah, I'm fairly,
The algorithm is called sure.
This was the case
No,
actually
if P
for.
doesn't equal NP, there's still an algorithm for factoring.
Yeah.
The fact that there's a quantum
But
one, it's the writing on the wall. There's a deterministic one. You just haven't found.
But this was the
I
case for the prime factor. The finding prime factors. It was believed to be NP, and then I think it was
So
4 years ago, 5 years
It's in
ago.
NP, exact co-NP, so most people believe that
What's in NP?
and so this
It's
factory.
a decision problem. It's
Yeah,
not a
it-
decision problem.
The
It's not
decision
a
problem that you
The
decide.
decision problem is in polynomial time. Primes,
She's talking about something else.
another problem.
So you're talking about primes that's in P.
Yeah, yeah.
You're talking about factoring, which is different.
Which is not.
It's not the same.
Factoring
So-
is to find the
Yeah.
decomposition in a prime factor of large numbers, and
So
that's
that we don't know
classical
what it's-
still NP. It's not NP
Well,
complete.
it's not a decision problem, so it shouldn't be an NP. NP is a decision class.
Okay, you can reformulate it.
What you mean is it's.
It'd be hard.
Well, it's not. No, it's not.
No, it's not NP hard. It's not NP hard.
No, it's just
No.
NP. It's not
You
even
can't
NP.
have a polynomial quantum algorithm for NP hard problem.
Yeah, that's.
No, this is not even NP complete. This
No.
is
No.
this
And
is a very, so to say, simple among the difficult problems.
It just can't be.
And but I mean, this was a good, a very important result. But since then, I think there were no other general techniques for designing quantum algorithms that are faster than classical ones. I mean, this is still the basic one. And actually, there is a full class of problems that you can solve, and it's called so all the problems that can be solved with the quantum Fourier transform and also the factorization can be reduced to the so-called hidden subgroup problem. Is a mathematical problem, and that's essentially it's the representative of the complexity of the problems that you can solve with this. Okay. But as I said, this is not an NP complete problem. So the question is still open. Doesn't solve the question whether quantum computation is more powerful than classical computation, because as Barney was saying, maybe tomorrow someone will find a classical algorithm.
Maybe for polynomial time, but there are concrete instances of problems that can be speeded up, like quantum computation.
Yeah, this is of course
quantum Turing machine can beat a Turing machine in certain things.
There's also a whole class that use the disparity between the quantum amplitude and the Born probabilities to give you a squared and n squared speed up. You know, not spectacular, but solid improvement over.
You can do even better than that, can't you, for some concrete problems? Better than
Oh yeah, no, this is just a whole
can-
class.
Yeah,
of
I
categories.
think this is.
You have such quantum search algorithm which can
That's a
have
square.
quadratic.
There is a Grover algorithm that is used for, it is practically very important.
Yes,
If
the
a quantum computer would exist, that would be, I mean, it would have an enormous impact also in cryptography.
And how much does it
Because
speed
you could search.
It's again a square root. It's again a square root.
A square root,
Okay.
You could search in an unstructured database with a speed up, which is the square root of, and this means that the length of your of the number that you use, for example, in RSA, must be much bigger than the one that is used nowadays. That we only have classical.
Yeah, and another thing that's got this kind of speed up is linear systems, solving linear systems.
Solving the
So that's an important algorithm as well.
Yeah. I mean, from the practical point of view, probably Grover algorithm is more important than.
So Grover algorithm is when the function is constant or not?
No,
that's
unstructured
just
database.
Is unstructured search. So basically exhaustive search when you have. So those are really the NP complete problem when you have to do exhaustive search and therefore.
I gave my students actually a graph of quadratic complexity, and I asked them to identify what it was, and one of them said exponential. So in some sense, you know, quadratic does look a bit like exponential, so an improvement from quadratic to linear is a huge improvement. So definitely quantum computation is more powerful than
No, especially also for practical
for practical
search or
very
linear
good,
equations.
Yeah. So that's the greatest challenge, to find other techniques. And from this point of view, topological quantum computation is very promising, and I will explain you why. I hope you will see why. So, in order to see this, I have to tell you about the Jones polynomial. Why? Because so first of all, does anybody know about? This is a mathematical problem, and the problem is to find knot invariants. It's an important problem in geometry. And the Jones polynomial was invented in 1984 by Von Jones. and it's a very powerful invariant, not invariant, in the sense that it is very, very good, so to say, at distinguishing nodes, because that's the main problem in node theory, to see whether two nodes are equivalent or not. And this Jones polynomial is the most powerful that we know at the moment. Okay, so now the problem is that calculating the Jones polynomial is very hard, and in particular, this problem is sharp P hard, which is much more than NP complete. It's a sharp P problem, and the best classical array is exponential, so is a problem that is not feasible with the classical computers that we have nowadays. Okay. Now, what is the great result that was invented, or reached some years ago? Maybe I think just a few years after the invention of this Jones polynomial. I think it was 1986, I think something like that. Witten, who is a physicist, has a field medal, and he got his field medal exactly for his work on
string theories.
And also for this topological quantum field theory. So he found this connection between topological quantum field theory and the Jones polynomial. And the connection is very strong in the sense that basically he gave an algorithm for computing the Jones polynomial, but just simulating topological quantum field theory. Okay? So this kind of algorithm that was expressed, so to say, in physical terms, was then rephrased in a computer science way, so to say, by Aronoff. So reformulated in terms of qubits, and the great result is that this algorithm is BQP as a complexity, which means bounded quantum polynomial, which means that can be calculated in polynomial time with the quantum computer. Of course, we are talking about approximating the result. So we are not talking about exact as always the case with the probabilistic algorithm. Okay. Now, why am I talking about this? Because this technique used here in this algorithm is not the quantum Fourier transform. Is not the Grover. Is none of the well-known quantum techniques that are used in the quantum algorithm. This is a very different because it is intrinsically a combinatorial technique that uses the topological feature and properties of some particular physical particles. So if we would get this physical particle work, then we would be able to compute the Jones polynomial and therefore solve Sharpie hard problem with a quantum computer. And that's why topological quantum computation came about. Actually, this is one motivation. The other motivation is related, as I said before, to the discovery of some very strong topological properties of some physical particle. Now, I just want to tell you something about topology that is very important that has an impact on this paradigm, computational paradigm, and this is that topology is I'll just read it. The part of geometry which survives deformation and perturbation. This means essentially that in topology you do not distinguish between the donut and the couples because you can transform this in this by continuous transformation. Okay, so there is no difference. So basically, this means that topological quantum systems, so if you can consider quantum systems that have these topological properties, then these systems are intrinsically resistant to perturbation, to local perturbation. And that's very important because one of the main problems, the main obstacles to build a quantum computer is the problem of correcting errors that that come out when you disturb the system. So because of this local perturbation, like measurements or any kind of external influence. So. As I said, it is the coherence is the main problem for building a quantum computer, and the coherence is exactly the one that destroys superposition and does not allow you to get the quantum interference, does not allow to exploit all these quantum phenomena that are the basis of the exponential speedup of quantum algorithm. Okay, so quantum decoherence essentially is the loss of coherence, and therefore it results after disturbing the system. And if you so as I said before, if we refer to the tree that I showed you before, this means essentially measuring or disturbing the system means that at each step the coherence of the system is destroyed because we measure it, and therefore we do not allow the amplitude to interfere each other, and therefore maybe ending we are not able to end with that result that I showed you before. Okay, so the coherence is the main problem for quantum computation, and it depends on this local interference and deformation of the system. And topological quantum computation was born because of an idea of Kitaev, who said this, which essentially says if we can exploit physical systems that are intrinsically resistant to local perturbation, so they behave topologically in the sense that the behavior is globally the behavior, the result comes from a global behavior and doesn't really matter what happens locally. So even if you disturb the system or you get this local deformation, that doesn't matter. So the coherence is essentially not a problem.
But this is not a fact. This is just a hypothesis. If it was
this was the idea. This was the idea that came because of the discovery of a particular behavior in some particular physical system. So there was an experiment that was called that is called the fractional quantum Hall effect, and this revealed the existence of some particles with these topological properties, and these particles were called anyons. Okay, and they a system of these particles have these topological properties, and therefore is resistant to errors. So if we could use these for computing, then we wouldn't need any error correcting code, which is something very, is the main problem now, because it's very expensive, it's very difficult, and I mean, it is already difficult, the classical correcting code, and the quantum are even more difficult and expensive.
Quantum means non-commutative.
Yeah.
And non-commutative means non-existence of conditional probabilities.
Mm-hmm.
So that means you cannot reason what is the probability of this property given that. Like, for example, you cannot say what is the probability of particle being in particular coordinate position if you know the speed. Given the speed,
actually,
there doesn't exist probability of
you cannot talk about probability, but we are really computing with complex numbers, and what we get as a result is something that is called a trace invariant. Is something like an average result. How can I say? What you get is you compute. I mean, I will tell you the.
We need to talk about it because I want to understand exactly because if there is a non-commutative observables, you cannot measure one or another. So I don't understand how.
This is more to do with entanglement density matrices rather than complementarity, which is I think what you're talking about.
The observables are quite different. You have to reason in a completely different way. So if you are used to think about projectors and defining, here we will define in a completely different way, because what we get, as I will show you, the computation is essentially braiding, and therefore the observables are the trajectories of these particles.
In continuous time.
Exactly, it's an adiabatic form of quantum computation.
So for this you need quantum stochastic calculus. Because then if continue in continuous
no,
time.
that's classical. I mean, you think too much of in classical terms, so you have to change a little bit.
But all quantum computing is adiabatic, isn't it? I mean, it has to be for the reversibility.
Yeah.
So, sorry.
There must be a reversible, of course, it must be a reversible computation, so you have to talk about unitary transformation.
Yeah. But that's true.
Contrary
but unitary
to
doesn't mean reversible. Unitary in Schrödinger does not mean irreversible in Heisenberg.
Unitary implies reversibility.
On infinite dimension. In infinite dimension, it could be
Yeah,
unitary in Schrödinger but not reversible in Heisenberg. Mm-hmm. And moreover, if dynamics is reversible in Heisenberg, then you cannot see anything. You only see 0 or 1.
In any case,